Hey everyone, and welcome! Today we're tackling a fun Leetcode problem called maximum erasure value. It sounds a bit dramatic, but the core idea is pretty interesting. We'll break down the problem, walk through some examples, and then build up to an efficient solution step by step. Let's get started. Okay, so here's the official problem description. The main goal is to find a continuous part of the array, a subarray, that has two special properties. First, all the numbers inside it must be unique, no repeats. Second, the sum of those numbers, which they call the score, should be as big as possible. Our job is to find that maximum possible score. So let's really break this down. We're given a list of numbers. We need to find a consecutive slice of that list. The most important rule is that inside that slice, no number can appear more than once. Once we find a valid subarray, one with only unique numbers, we calculate its score by just adding up all the numbers inside it. Since there could be many different unique subarrays, we need to check all of them and find the one that gives us the highest possible sum. That highest sum is our answer. All right, let's walk through the first example to see this in action. The input list is 4, 2, 4, 5, 6. Let's start from the very left. A subarray of just 4 is valid, and its sum is 4. Let's expand it. 4, 2 is also valid, sum is 6. Now we try to expand again to include the next number. 4, 2, 4. Oh, we have two 4s. This is not a valid subarray, so what's our next move? Since 4, 2, 4 was invalid, we have to fix it. The problem is the duplicate 4. The simplest way to fix it is to get rid of the first 4. So we shrink our window from the left. Our new subarray is 2, 4. Hey, that's valid again. Now we can continue expanding. We add the 5. 2, 4, 5 has a sum of 11. Still good. We add the 6. 2, 4, 5, 6 has a sum of 17. Awesome. We're at the end of the list, and the highest score we managed to get was 17. This process of expanding from one side and shrinking from the other should ring a bell if you've done similar problems. It's a perfect fit for an algorithm pattern called the sliding window. We use two pointers, a left and a right, to define the edges of our current subarray, or our window. We slide the right pointer to grow the window, and if we ever break the unique elements rule, we slide the left pointer to shrink it until it's valid again. So what tools do we need to build this? First, we need our two pointers, which we can call left and right. The right pointer will just move through the array one step at a time. To quickly check if a number is already in our window, a hash set is the ideal tool, because adding, removing, and checking for an item are all super fast, basically instant. We'll also need a variable to keep track of the sum of the numbers inside our current window, and another one to remember the best score we've seen at any point. Okay, let's put it all together into an algorithm. We'll start everything at 0, the left pointer, the current sum, and our max score. Our set of seen numbers will start empty. Then, we'll loop through the array with our right pointer. At each step, we look at the new number. Here's the crucial part. If we've already seen this number, we enter a little inner loop. This loop keeps shrinking our window from the left. It subtracts the leftmost number from our sum, removes it from our set, and inches the left pointer forward. It does this until the duplicate is gone. Once the window is valid again, we add the new number from the right, add its value to our sum, and update our best score. We just repeat this until we reach the end of the array. And here is the complete Python code for that logic. You can see all the pieces we just talked about, the set called seen, the left pointer, the current sum, and the max score. The main for loop iterates with the right pointer, and that while loop inside handles shrinking the window whenever we find a duplicate. Finally, at the end of each step we update our max score. Let's look at the setup. We create an empty set called seen to store the numbers in our current window. The left pointer starts at the very beginning of the array, at index 0. And, of course, our current underscore sum and max underscore score also start at 0, because we haven't processed any elements yet. The engine of our solution is this for loop. The right pointer will move from index 0 all the way to the end of the nums array. In each iteration, right represents the right edge of our window, which we are trying to expand. This is the most important part. Before we add the new number at the right pointer, we check if it's already in our seen set. If it is, we have a duplicate. This while loop then kicks in. It removes the element at the left side of the window from our sum and from our set, and then moves the left pointer forward. It will keep doing this until the duplicate that we're trying to add is no longer in the window. After the while loop finishes, we're guaranteed that our window is valid, so now we can safely expand it. We add the new number from the right pointer into our scene set and add its value to our current underscore sum. Then, we do a quick check. Is this new current underscore sum the biggest one we've seen so far? If it is, we update our max underscore score. So how efficient is this solution? For time complexity, it's big O of n, where n is the number of elements in the input list. Even though there's a loop inside a loop, notice that both the left and right pointers only ever move forward. Each pointer will touch every element at most once, making it a single pass through the array. For space, it's also proportional to the input. In the worst-case scenario where every single number in the array is unique, our scene set would have to store all n elements, so we say the space complexity is big O of n. So to wrap things up, the main takeaway here is recognizing the sliding window pattern. When you see problems about finding an optimal subarray or substring that follows certain rules, a sliding window should be one of the first things you think about. Using a hash set to keep track of what's in your window is a super common and effective trick. And remember the main idea. Always try to expand your window and only shrink it when you absolutely have to because you've broken a rule. I hope that breakdown made the solution clear. If this video helped you out, I'd really appreciate it if you hit the like button and maybe subscribe for more Leetcode explanations. If you have any questions or a different way to solve it, drop a comment below. And hey, if you're feeling extra generous, there's always the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.